Okay, good day, everybody. So today we are going to do the last section for Unit 4 before the break. It's about graphing stuff again, so very much easy things again, so we can coast to the final. All right, warm up today, though, is just some more word problems. They're actually not going to take that long. Number one is asking, reasoning, describe the end behavior and the possible degree and sign of the leading coefficient of the graph shown. So if you look at this graph, what's it look like? Does it look more like an odd degree or an even degree? Anybody got any suggestions? It looks more odd, I agree, yeah. As a refresher, evens all look the same on the sides, right? Both sides would go up. Odds, one side would go up, the other side would go down. Now, it doesn't look exactly like an odd because what's the difference here? Odds usually start in the bottom left, right? Go to the top right. This is completely flipped. So how do you flip something? You put a negative in front of it, correct? So I'm thinking this must be an odd degree, and the leading coefficient must be negative. That's your answer. Write it down. We're done. That's it. Showed us this graph. Copy down the graph too, kind of like get some humps. Don't really care about the humps. I don't care what's going on in the middle. I care about what's going on the ends. Today we'll talk about the middle. You know, finding the humps and the extrema and all that kind of jazz. But mostly you just want to be focused on the ends. That's what you should know right now. All right, that's it for number one. Number two is saying explain why a polynomial function with an odd degree must have at least one real zero. Well, we kind of got one on the board already. The graph from number one counts for this as well. This was an odd degree, correct? Why does it have to have at least one real zero? Remember, a zero is where it crosses the axis, correct? So there's got to be one real spot where it crosses the axis. Why? Well, if one side starts on the bottom and the other side goes to the top, doesn't it have to cross somewhere? That's kind of the answer right there. I don't know how you want to write that, but that's the answer. One side goes to negative infinity, the other side goes to positive infinity. They go to opposite sides somewhere in between them. It must cross the axis at least one time. Maybe it crosses 3 times. Maybe it hits it twice. You don't know. But dang it, it's got to be at least once because it does go from bottom left to top right, or vice versa. If it was going from top right to bottom left, same kind of exact arguments there. Okay, so that was it. That was an easy warm-up. Nice and short and sweet today. That was good. Let's do some LGs and get ourselves to work. Here we go. Learn to approximate zeros, find extrema, which you already know how to do. This is nothing you haven't already done. You're just doing it with polynomials instead of quadratics. You can find mins and maxes. You can do second calc and figure out where it crosses the axis and find a zero. That's all today is. If you haven't noticed, every single unit or topic we have seems to have 2 flavors to it: graphs, straight up equations. I always start off talking about the graphs and what things look like, and that's very, very important. And that's what we're still stuck on today. When we come back from break, when we finally resume this unit and way in the future, we will be focused more on the algebraic side of things, how to solve equations with these things. But every test is kind of the same thing. Oh, look at that. Sherry's alive. Look at that. Yeah, how are you doing?
Alive, so problem.
Problem? Yeah, that does suck. You guys need more time?
Last week we did the review and tests.
Yeah.
How are you gonna want me to do that?
Whenever you're ready, I got it right here with your name on it.
Should I have to do the review too, or?
I can exempt you if you want, but I would do it. You know, it's like the test. So.
I have to go take a review.
Reviews on Google Classroom if you want to do it. If you don't, I'll exempt you, but I would at least look at it. I mean, it's the same thing as the test. So. Okay.
Because the review was on paper.
It is. So it's test.
The review is on Google Classroom.
You can print it off. There you go. Thanks, Cherry. I'll see you later.
Oh, he's even using Cherry now.
Yeah, there we go.
Right.
That's what he wanted. He told me that day one.
My boss told you that.
He told me to call him that. All right, here's a new one, 4-2. Write it down real quick. Page 229, 1 through 10, 16 through 19, 21 through 26. Due Friday, got 2 days. Tomorrow you got a work day again. I don't think you're going to need it. I think like yesterday was kind of overkill with work time because it was an easy assignment. I anticipate the same thing will happen on this one. That's okay. Still got your work time. So easily can get it done. Friday, we'll start to review for the final. And I'll give you a big fat review packet. It's going to be just wonderful. All right. Notes today. We're in section 4.2. Let's get a title going for that. Here it is. Analyzing graphs of polynomial functions. It's found on page 223 of your book. It's pretty self-explanatory. Analyzing graphs, there's only so many things I could ever ask you to do. I could ask you to find domain and range. I could ask you to do increasing, decreasing. Eventually something called concave up and concave down. But a couple other things I would ask you to find are extrema and zeros, and that is the topic of today. So here we go. You have to write this down. It's common sense. It's something called a location principle. All this thing means is, if on some number the graph is negative, by that I mean below the axis, correct? And some other number, it's above the axis, so it's positive, right? Well, just like we talked about the cubic, if one side's going up and the other side's going down, what? It must cross the axis somewhere, correct? Well, that's all this is saying right here. So it says, if it's negative on one side and positive on the other side, then somewhere in between must be zero, and we can locate, there must be a zero in there. That's the location of it. That's why it's called the location principle right there. All right, get your calculators out. Let's do this stuff. Example number 1, locate zeros of a function. That just means where it crosses the axis, correct? So you have bigger things to type in, but go to y1 and type in this equation right here, x to the 4th minus 2x cubed minus x squared plus 1. Now your homework and the textbook asks quite often to make a table. I really don't care if you make a table, okay? So if you want to make a table, go ahead. You don't need to. What's this table say? If you were to take numbers and plug them in tediously, -2, if you plugged it in, you'd get out 29. Take -1, plug it in carefully, you'd get out 3. Do you see anywhere where the value of the function, the bottom line, changes from positive to negative? I see right here. Do you see it changing from 1 to -1? So it changes sign. So somewhere from x goes from 0 to 1, there must be a 0. It must cross between 0 and 1. Do you see any other spots where the function changes sign? Here it's negative, and then it changes back to positive, correct? So somewhere between 2 and 3, there must be a 0 also. So if you want to make a table like that and see where the signs change, be my guest. I'd much rather you just kind of graph the thing. If you graph that, you should see something that looks kind of like this red one. Do you see something like this red one? Sweet. All right. So how do you find zeros again? Well, first of all, what's a 0? It's where it crosses the x-axis, right? I see 2 spots. You see 2 spots? Let's go find them. Second calc, 0. And you know how to do it. Left bound, anywhere to the left of where it crosses the axis. Right bound, anywhere to the right of where it crosses the axis. Guess doesn't matter. And as promised, there's a number between 0 and 1. That makes it a 0, and that's it right there. Write it down. There's a 0 at 0.72ish. You don't have to write down every decimal. Please give me a couple, though. What that number is, I have no idea, but that's the answer to the problem. You do the same thing for as many as there are. If there's more than 1 0, you just keep doing it. Second calc, 0, up, there's one over there. Anywhere to the left of it, it really doesn't matter. I'm definitely to the left of it. Right bound, anywhere to the right. The guess doesn't matter. The other answer apparently is 2.34ish, 2.35 if you round or something like that. Make sure you can find these. If you can find them, then you can type things in correctly. You can do second calc correctly, and you'll get your homework correctly. So if you can do this in the thing we're doing now, you'll be just fine then. Again, I do not require you to do a table. If there's a question online where they want you to fill out a table, I guess you got to fill out the table to get the credit for it. But for me and the handwritten work, you do not need to do any tables. It's that simple. No big deal. Let's try another one. Determine the consecutive integers. So find 2 numbers in between which these zeros are located. So go back to y equals, clear it out. Type it in just like it looks. Normally, your normal window, the -10 to 10 will cut it. Sometimes you will have to adjust your windows, but most of the time, Zoom 6 reset to the standard window will do just fine. 2x to the 4th. Remember your power button's over there by the clear button. That caret thing is your exponent button. Once you got it typed in, hit Zoom 6, reset your window. And as promised, you see, here it comes. First of all, does this graph make sense? Does this look like a fourth degree problem? This is a fourth degree. It looks like it should. Yep, both ends go up. Everything's cool. I see 2 zeros again. Let's go find them. Second calc 0. I'll take the one on the left. Anywhere to the left, anywhere to the right. First answer is negative 1.64. And I would always like you to get the exact answer. On your test, I will never ask you what two numbers it's in between. There's no real point for that, but they might. What two integers is negative 1.64 in between? Wouldn't you agree it's in between -2 and -1? So for them, you'd say between -2 and -1, that would be the two integers it's in between. And same logic for the other one. Second calc 0. Cheney just wants the answer. He doesn't care what two numbers it's in between. That doesn't help him much. So a Cheney answer would be 1.238-ish, something like that. I'm not going to harp on sig figs or anything like that, or like, oh, I should round to the thousandth or something. I'm not going to do any of that. Don't worry about that. There's one answer, and then the book would want what two numbers it's in between. Well, 1.2 is between 1 and 2, correct? So you'd say between x equals 1 and x equals 2. So very straightforward, isn't it? Nothing too tricky at all so far. The only other thing to talk about is extrema of polynomials, and I would like you to write one thing down for you. This is your notes. And this last sentence right here, the graph of a polynomial of degree n, an nth degree polynomial, has at most n minus 1 extrema. That is one concept I'd like you to put in your mind for the day. The rest is just doing calculator stuff. For example, I really want you to think about this and have it make sense to you. You look on the board right here, I put up lots of different polynomials. Some are really basic ones that we've studied. Some are getting more complicated. We studied lines before. You did that in Algebra 1 to death, right? Like here's a linear thing or something like that. It is a polynomial. It can be written as many terms kind of add together. What degree is this? It's a first degree, correct? Okay. Now, how many extrema do you see? How many humps do you see on this graph? None, right? There's 0. So you're for a first degree, how many extremas does it have? It has 0 extrema. Oh, okay, one less, right? One less than the degree. Over here, we just got done saying quadratics. That's a second degree, correct? So if the second degree thing, they always have how many humps? They always got 1, right? Yep, either opens up or down, but there's 1 hump, so there's 1 extrema. Here's a third degree. How many extrema do you see? 2, 1 less, correct? Now, the key word here also in the notes is it can have at most n minus 1 extrema, at most. That's a key thing. You might even underline the word at most or something like that. It doesn't have to have that many, but that's the most it can have. For example, a simpler cubic, just y equals x cubed, it has absolutely no extrema. There are no humps for it. So it's a cubic. How many could it have? It could have 2. Does it? Not always. So that's the thing about at most. So you understand that thing there? Here's an example of, I don't know, what degree could this be? I didn't mean to go that many humps. How many humps do you see? 1, 2, 3, 4, 5, right? This could be a what degree then? It could be 1 higher, right? It could be a 6th, right? So if I see this, you can look at the humps and kind of estimate what degree it might be. But a 6th degree could look like this. It could have no humps, correct? Or 1, right? It could have less than that too. So that's the key thing I want you to remember about that. All right, beyond that, all you got to do is find them with your calculator. Nothing too tricky. Let's do the thing where we do that. Use a table to graph this. I don't think we're going to do that. Let's just graph it. Okay. You'll never have to do a table if you don't want to. So go to y equals and type this thing in. X cubed plus x squared minus 5x minus 2. Estimate the x coordinate at which the relative maximum and relative minima occur. That just means local, okay? Just where the humps are, essentially, right there. And notice again, they say estimate the x coordinate, and that's a reminder to you. I only want the x's. I don't care how high it is. I'm always obsessed in this class about where things are happening on the x-axis. If you want to figure out the y for anything, you can just go plug the x into the equation, right? So we never really care about the y's. We just want the x's. Okay, once you type that in, let's see what we got. Did it fit in the normal window? Do you see something that should look like a cubic? A cubic should start in the bottom left, right? Go to the top right. Does it? Let's find out. It sure does. There's my cubic, as promised, just like the graph shows there. This time you're looking for extrema. Now, this one over here is on a max, right? So make sure you go to second calc. Make sure you pick max for that one, because or else it's not going to work. Left bound, same thing. Go anywhere to the left of the hump. Right bound, anywhere to the right of the hump. Guess does not matter. And you would tell me that there's a local max. Do you remember your terms local and global? Do you remember that stuff? Local, always a local extrema. As a refresher, the book might say relative extrema. So I did define it both ways when we first learned that. I said, okay, they might say relative. I'll say local. It means the same thing. Relative means local, in case you forgot that. Is it a global max there? No, it's not the highest spot ever. So they might use the word absolute max for that, by the way, too. So just remember, as a refresher, relative means local, absolute means global. But there is a relative max at x equals negative 1.66, and that's what you write down. Don't even tell me the y. I don't care what the y is. Don't tell me that. I don't care. What about this one over here? It's a min, right? So do the same kind of logic. Second calc, but just select minimum. Go anywhere to the left of where that bottom hump is. My cursor's to the left of it. That's great. Right bound, go anywhere to the right of it. Hit enter. Guess doesn't matter. And 0.99999. Now, if something's ever that close to a pretty number, guess what? It's just a pretty number. So you could tell me that there is a local min at x equals 1. It's so close to 1, you can assume that that's a rounding error right there. Does it make sense that there could be 2 humps for this degree? The third degree, right? You could have 1 less than it, which is 2. So it is possible to have 2 humps in this particular equation right there. And that's all you're going to be doing in this assignment over and over and over again. Let's do just one more for fun. Here's a real-world problem. Pilots. The total number of certified pilots in the United States is approximated by this function. It's a big, long thing and a pain in the butt to type in, but we're going to do that. This is example 3 in your book, where x is the number of years after 1930, and it gives the number of pilots in thousands. Graph the function, describes key features over the relevant domain. Okay, so step 1, go graph this thing, which is a big pain in the butt to type in. Let's see if we can do that right, because that's hard right in itself. Check every little dumb number. Down here, I kind of got it in my calculator already. There are 4 zeros after the decimal on this first one. 0.1234 zeros. And then 903x to the 4th. After that's not so bad, just type in a lot of digits. Minus 0.0166x cubed. Plus 0.762x squared. And then plus 6.317x and an additional 7.708 thrown on the end. This is a 4th degree. I might expect 3 humps. That's very possible to find 3 humps. I don't know. It is possible to have 4 zeros. Here's the key thing about this. Whatever the degree is, that's how many zeros there could be. And 1 less than the degree is how many extrema there could be. Once you got typed in, hit zoom 6. I really don't think that's going to be a good window in this context. X represents the years after 1930. So let's see here. If x was, this only goes to x equals 10. That would only be 1940. You probably want to go a lot farther out than 1930. How about let's change our window. Let's see, how many years past, what is it, 2020 now? So how many years has it been since 1930? 90 years? So let's have x max go to 90 because x represents how many years after 1930. Speaking of, it doesn't make sense to have negative years after 1930. We're starting this experiment at 1930, so you might as well have this be 0. This is a more realistic window right here, going from x min from 0 to 90. That means our thing will start basically in 1930 and go all the way up to 90 years after that, present day. What about y stuff? Y is what you get out. Remember, this is a function that describes the number of pilots. So does it make sense to have a negative number of pilots? No, I would say that my y min should be 0. And the y max, I'm really just not sure. This will represent the number of thousands of pilots. Do you think there's only going to be 10,000 pilots since 1930? I don't think so. Maybe 100,000, million, I don't know. I'm going to go to y max being 100. If that doesn't work, we'll just come back and tweak it. Do not hit zoom 6 after you've changed your window. That'll just change it back to what you had. Hit the graph button at the top right. Oh, look at that thing. It's just shooting up and shooting up and shooting up. It's going really high. But I guess there's a lot more than 100,000. Let's go back to window after it gets done graphing. Man, 100 does not cut it. I'm going to add on a couple more zeros. I'm going to go crazy on this thing. If that's overkill, then I'll come back and adjust it some more. Oh, look at that weird thing. Okay, looks like I went too high now, right? It's kind of wiggling and then leveling off something. So maybe that was one too many zeros down at the bottom. I'll take a 0 out. By the way, there is a delete key right here, right next to your arrows. You can just hit that on a character and it'll go away. So I'm going to go to 1,000 instead. That looks pretty good. I like that right there. That's a pretty good picture of what's going on. So kind of draw a rough sketch of this for this thing. Now we don't have to worry about anything that doesn't make sense. Here, time is positive, and here's the number of pilots is positive. Everything's okay. What seems to be some key features? I do see an extrema right here, don't you? Let's go find that extrema. Second calc, max. That's a max, so anywhere to the left of it. Scroll over or anywhere to the right. And I'm getting a max at about 54 or something like that. So you might want to write down there's a local max at x equals 54.39 or something like that. What's that mean? Remember, these x's in this problem stand for the years since 1930, right? So if x is 54, 54 years after 1930 is 1984. So this is an Orwellian kind of thing, I guess. So what's happening? The number of pilots is increasing until 1984. Would you agree? Then the number of pilots seems to go down, and there seems to be another minimum right there, which you could go find as well. You could do second calc, find a min or something like that. But you have to interpret in terms of the problem. I guess the number of pilots was increasing until 1984. Then they had a slight dip in it. I don't know why. Maybe voodoo economics or a Reagan policy. I don't know. All right, that's it for today. So your homework is 4.2, due on Friday. 4.1 is due today. You guys got plenty of time to get those taken care of. Very much graphical and easy kind of stuff. Main highlight from today is the number of extrema could be at most one less than the degree of your problem. All right.